Let us talk about semilog graphs. Semilog graphs are a very useful invention for trying to work out parabolas and things, and trying to turn parabolas into a straight line. One of the skills of an experimenter is basically to turn any data set they get into a straight line, because if we have a straight line graph, we can make very easy predictions. We can put a value here of x, we can pull out a value of y. And this allows us to make predictions about future events, because we can just follow the line further down and make the prediction there. Now what we're going to do, you'll know the whole point of using a log graph, you'll notice on this axis, this is a logarithmic scale. It's got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and that repeats. 1, 2, 3, 4, 5, 6, 7, 8, and you can have another set or more. So this has got two, we call this a decade. This one's got 2 decades. You can get graphs with 3, 4. And the thing about this is set up as a logarithmic scale. So when you're entering this data onto the graph, you don't have to take the log values of these. You can just use these numbers straight, put them in the graph, and the graph will do the work for you, will do the mathematical work for you. So this is rather quite a cool invention. So what we can see here is normally it's, this could be, so each of these is going to represent a power of 10. If I were to write a number, I can write a number like 6 times 10 to the 1, and that would represent 60, for example, or 5 times 10 to the 2, and so on. So this number here, the 6 and the 5, are these digits here. This power here is which decade it's in. So, let's take an example. So this could be set up, so it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 20, 30, 40, 50, 60, 70, 80, 90, 100. But you'll notice my data set goes from 50 to 117. So it's probably better to start off as 10, 20, 30, 40, 100, 200, 300, 400. And that's why I've written down here times 10 to the 1. That says if we multiply this digit by 10, this times 10, so that says we multiply that digit there by 100. So when I look at this, I look at my first piece of data and it's 117. So the time is 0, the data is 117. So I look up here, so 90, 100, 100 to 200 here. So each of these little lines between there is going to be around 105, so 17 would be about here somewhere. 105, so we go along 15, go up to 105, so 100, up one little line. 99, so I'm at 30, I go up, and 99 is going to be just under that 100 line, so that goes in there. 45 seconds, we go up to 90, well that 9 times 10 is 190, so that goes there. And so I then enter all my data points without converting them. That's the important thing, the graph paper does the work for you. And then like any other graph, when I take the raw, once I've got the data points, I choose 2 points, draw a line straight through it. In this case I chose the first point and the last point. This becomes important when you're trying to do your scale, work out your gradient. So let's work out the gradient. So I've chosen point 0, 117 time, and for point 2 I've chosen that 150 seconds, the value is 50. Now to find the gradient, normally to find the gradient, what we'd do is we'd go y is equal to, m is equal to change in y over change in x. In this case we're going to go m is equal to natural log of the change in y over change in x. Notice we only take the natural log of the y value because that's the only one that's done as a log. And then what we do, so that's going to be equal to natural log of y2 minus natural log of y1 over x2 minus x1. So the time is on the x-axis, so this is going to be x. Okay, and so time is going to be x, and the count is going outside, so that's going to be y 0 is my first point, and 150 is my second point. So what I have to do is I have to take the values of these two. So this is going to be, I'm going to take the natural log of y, so I'll just use a calculator. Okay, so natural log of 117 equals 4.762. Natural log of 50 equals 3.912. So now we take the natural log of y2, so that's y2, it's 3.912, minus the natural log of y1, which is 4.762, and we divide them by x2, 150, minus the y1, x1, which is 0, which equals, so we just stick this through the calculator, 3.912 minus 762 equals, divide that by 150 equals minus 0.005667. What's that negative tell us? That tells us it's a downward slope. Now the next question, of course, is how do we work out the intercept? And the easiest way to do that is just read the intercept off the graph. So when this is at 0, we just literally just read it straight off the graph, and in this case you'll see the constant equals 117, because if I just read that off the graph, it's going to be that point there, 117 counts per second. So yes, this is a very, very useful tool for just turning a parabola into a straight line, which we can then use, and we can then use this to find out the gradient.